classify all the critical points of the nonlinear system. So the first thing that we look at is this matrix over here, and that is our Jacobian. Now we want to evaluate it at each of the critical points, because remember, that is a linear planar approximation, local planar approximation of this nonlinear system of differential equations. So what I'll start with is I'll start with my first critical point, the Jacobian evaluated at 0, 0. With the Jacobian evaluated at 0, 0, we're going to have 0 minus 2 times 0 plus 1. So we're just going to have 1 here. Then 0 minus 1, we're going to have a negative 1 here, a 0 here, and a negative 1 here. Now, what do we expect the 0, 0 to be? It should be some sort of sink, because it's an attractor always, the 0. So let's see. If we find the eigenvectors, we get 1 minus lambda times negative 1 minus lambda minus negative 1 times 0 should be equal to 0. So if I factor out a negative sign, I get, well, we don't even have to do that. This is 0. So either this is 0 or this is 0. If we set each equal to 0, we get what? We get that lambda is equal to 1 or lambda is equal to negative 1. And because they're of opposite signs, this is a saddle. So I take that back. I said it's always an attractor. I guess not. I guess if you start at 0, you won't go anywhere, and that's why it's a critical point, but it's not always an attractor, so don't mind what I said earlier. Now, the Jacobian needs to be evaluated at our other critical point, which was negative 1, negative 1, right? Let's see. Negative 1, negative 1. So what is that going to be? Well, we're going to have negative 1 plus 2 minus 1. So this is just going to have a 2 here. This is going to be negative 2. This is going to be 2. And this is going to be negative 1. Now, if we find the eigenvalues here, we're going to get 2 minus lambda times negative 1 minus lambda minus negative 2 times 2. That's equal to 0. So factor out a negative sign, lambda minus 2 and lambda plus 1 times negative 1. This becomes positive 4 equals 0. This cancels with this, and we get lambda minus 2. Well, we have to multiply this out. So we get lambda squared. The sum of the two constants is negative 1 times lambda minus 2, the product of the two constants, plus 4 equals 0. Now we're going to have lambda squared minus lambda plus 2 equals 0. Let's try and complete the square. So we're going to have 1 over 4. So, hold on. So this is 1. We need to divide that and then square it. So we get 1/2 or negative 1/2 squared. That is plus 1/4. But you can't just do that to one side of the equation. You have to do it to both. Now let's bring that 2 on the other side. And this can be factored as lambda minus 1/2 squared equals minus 2 plus 1 over 4. So now we get let's take the square root right away. If we take the square root, and we'll make this, instead of 2, we'll make it 8 over 4, which is the same thing. So minus 8 over 4 plus 1 over 4, that's minus 7 over 4. So lambda, and remember we're taking the square root, so lambda is equal to 1/2 plus or minus here, plus or minus the square root of 7i over 2. So we have a positive real part and an imaginary part, which means that this is going to be an unstable spiral. Unstable spiral. And now we're going to be looking at the last one. So that's going to be, I don't remember what the critical point was, 1, -1. So here we're going to evaluate the Jacobian at 1, -1. And so what are we going to get? We're going to get, so -1 minus 2, that's going to be -3 plus 1, that's going to be -2. And then 1 minus 1, that's 0. -2 times 1, that's going to be -2, and -1 over here. So finding the eigenvalue, we get, this is -1 minus lambda minus 0 times -2 equals 0. This goes to 0. All we're left with is that lambda must be equal to -2, or lambda must be equal to -1, which means since they're both negative, this is going to be a stable node. And we know they're not imaginary, so they're not going to be spirals. So now we can classify them. We can say 0, 0 is a saddle. Then we have -1, -1 is an unstable spiral because it's got that imaginary part and the real part is greater than 0. And the last one, 1, -1, is a stable node. Now I'll show you real quick how you can do this very fast in MATLAB, and I'll see you there.